Okay, welcome to class. Welcome to class. Microphone volume works. Okay, go ahead and get your clickers ready. Session ID, channel ID is up, and the first question is available, which is what kind of defect involves both a cation vacancy and a cation interstitial pair in a ceramic? Is it a self-interstitial, a Schottky defect, or a Frenkel defect? Okay, answers in A, B, or C. Okay, we're going to go to our next question. Was this self-interstitial, Schottky, or Frenkel? People vote Frenkel. Let's see, which one is this? This one, it is a Frenkel. That is a Frenkel defect. Okay, why do we alloy metals? To improve electrical conductivity of the pure metals, to improve mechanical strength and corrosion resistance, or to create, missing an E, rad heavy metal music. I'm realizing now that I forgot to tell the program which one of these is correct. I can do that afterwards, so it won't show you the right answer because I forgot to put it in yet. But you'll get the correct points for it after I input it when the class is over. Okay, A, B, or C, answers in. Okay. Last question. Yeah, that's a no-brainer. Hey, we did it again! Twice in a semester. Well done. That's amazing. Okay. Which of these are interfacial defects? External surfaces and twin boundaries, grain boundaries and phase boundaries, stacking faults, or all of the above? It's a pretty good guess. Okay, wrapping up. Answers in. Okay. Definitely all the above. Okay. Okay, what are we going to cover today? Last time, all we did was introduce the idea of vacancies. We talked about that there's an activation energy for them, that it's a thermally activated process, and we did our very first calculation where if I give you an activation energy, you could actually calculate how many of these things exist per unit volume. We did it per cubic centimeter, right? In fact, we compared that to the theoretical versus the observed density, right? The theoretical density of copper should be 9.06. The measured is 8.96. And we said maybe, at the end of last class, we said maybe that these vacancies are part of the reason for why this discrepancy exists. You're actually going to further answer that question on the homework, right? You're going to determine, is it due to the vacancies or is there something else happening, and what's the fraction, right? What's this discrepancy due to? Can we really chalk it up to vacancies, or are they a small contributor? Okay, today we will talk about what are Schottky and Frenkel defects, which are kind of like vacancies, but they're more complex. They're two defects in one. And in doing so, we'll talk about defects in ceramics. We'll describe how thermal expansion can be considered in terms of vacancy formation. We'll talk about a few of the basic important alloys out there, and then we're going to move away from zero-dimensional defects to one-dimensional and two-dimensional defects. And by the end of class today, if we have time, we'll even talk about some of the tools that have been created by scientists over the years to actually try and observe these defects and quantify them, right? So if you're talking about a single missing atom, how do we even know that it's there, right? How do we probe these things, okay? So let's pick up where we left off then. We finished talking about vacancies. Now let's talk about self-interstitials. A self-interstitial, this is when an atom crowds into an interstitial site, but that's not where the ion is normally at, right? So in this picture here, what sort of defects do we see, right? In site number 1, that's this top one. You've got site number 2, that's this one right there. You've got site 3, site 4, and site 5. You have lots of different defects. Thank you, new computer. Telling me how to use my pen. Right? So clearly site number 1, let's change color. Site number 1 is a vacancy. That's where an atom should be, but it's missing. That's this one up here. You can have a self-interstitial, which is where an atom shouldn't normally, but it's crammed in there. So where's that happening? That's number 3, this blue one, right? So that's our self-interstitial. So since you're talking about an atom fitting where it shouldn't be, these typically, self-interstitials tend to be smaller atoms. And the word self-interstitial actually means it's of the same type. So in a metal, technically 3 wouldn't be a self-interstitial, that would just be an interstitial. A self-interstitial would be an atom the same size as the gray ones, right? So that's not actually drawn in this figure here.
Number 2.
I drew actually right next to it. Yes, that is a self-interstitial. Need my eyes checked, right? So 2 would be the self-interstitial. 3, the blue one, would just be what we call just an interstitial atom, right? Interstitials are common. Things like hydrogen or carbon, really small atoms tend to be interstitials because they can fit in the gaps between other things, right? All right, then you've got 4 and you've got 5, and those we would call impurities, right? They're different types of atoms. They're different sizes. One is too small and one is too large. Both of those cost the system energy, right? The strain field around that impurity is either going to be in tension or compression, and compression always costs more energy, okay? To push atoms, to squeeze them together, costs more energy than to be pulling them slightly apart, right? So therefore, would a vacancy or a self-interstitial have a larger energy penalty? Is our next clicker question. Okay, answers in. Self-interstitial versus vacancy. Which one costs more energy? Okay, we're going to wrap it up. Yeah, definitely it's going to be self-interstitial. And the reason why is because it creates much more strain. To try and cram an extra atom in there is pushing the other atoms apart. They'd way rather have a missing atom and have a dangling bond than be compressed together and strained, right? All right, self-interstitials do exist. It's possible that they exist. But since they cost more energy, they're going to have a higher activation energy, right? And our expression for these things, the number of defects, is going to be a function of how many sites there are times the exponential of our activation energy divided by our thermal energy, KT, right? So if Q, our activation energy, gets really, really large, then you're going to have fewer and fewer of these things, right? Therefore, the number of interstitials will be less than the number of vacancies because it just has a higher activation energy. So those were in metals so far. We can shift gears and now talk about ceramics. In ceramics, we're typically talking about things that have cations and anions, right? So positive and negative charges. So if I were to take out, like, say in this picture here, right? If I take this atom out, if this was a positively charged atom, now overall our crystal is overly negative, right? Because I took out the positive atom, so it's overly negative. So charge neutrality always has to be maintained, right? Because of that, there's many, but we're going to talk about 2 in this class. There's 2 important types of defects that form in ceramics. The first is called a Frenkel defect, and the second is called a Schottky defect, right? So a Frenkel defect is a cation vacancy and a cation interstitial. So basically, your cation, something like, let's say you're aluminum 3+ in your Al2O3, it leaves the site where it's normally at, creating a vacancy, but all it really does is it moves somewhere else in the lattice nearby. right? So it's going to create an interstitial. Whereas a Schottky is going to have the cation vacancy, and it's going to be offset by an anion vacancy, right? If they're both the same charge, there'll be one of each. If they're different charged, then there might be different numbers of vacancies to account for charge neutrality, okay? So how you're going to remember these is up to you. I think that Frenkel kind of sounds like Frank, kind of sounds like a creepy name, kind of sounds like a guy who doesn't respect your personal space, right? And this cation is not respecting personal space. However you want to remember it, that's what I do, okay? So again, you can see these here. One of these is a Frenkel defect, one is a Schottky. Which one's which? Turn to your neighbor and which one is which? Right? The one on the left clearly is the personal space invader. That's our Frenkel defect. The one on the right, so it created a vacancy. That's where it came from, and now it's sitting right there. This one created a vacancy, now it's sitting right there. So it has two Frenkel defects. Here you've got one missing green atom, one missing red atom. That's a Schottky. Okay? All right, how about this? Group question. If you take an atom from the center of a material and you move it to the surface, should there be a difference in energy? What do I mean by that? So let's imagine Ryan is my atom, right? I pull Ryan out and I create a vacancy where Ryan used to be, and I have him sit on the surface. I create a new row. I put a new chair there, and I say, now you're going to sit on the surface, right? Same energy, different energy. What do you think? Discuss with your neighbor. Okay, what do we think? Let me pick on, is it Allie? What do you think? You think might go up in energy. That's a good question. We haven't quite answered. So there is a difference in energy, but I guess we could argue going up or down. Somebody argue going up. Allie, what's your argument for going up in energy? Not sure. Yeah, behind you.
I'll argue going down.
You'll argue that it goes down in energy. What's your argument?
There's less bonds on the surface. When it's in the middle, it's got bonds all around it, but on the surface, it's got them.
And bonds usually make things happy, though, right? So let's take somebody who has 6 neighbors, right? Matt. Matt has 6 nearest neighbors. Well, if you count as one, I'm showing this. Right now, he says 4, right? So if I pull Matt out, then now there's 4 broken bonds, right? And I put him on the surface, and if I put him next to, what's your name? Joseph. Now we created 1 bond, but we broke 4. So that actually, that hurts us in terms of energy, right? That doesn't improve things. That makes energy worse. We went up in energy, right? So if it always costs energy, should this ever happen? Well, we know it happens. So what's the other argument? Somebody want to argue why it goes down, right? Rob?
Well, I would just argue that why it could happen is because maybe you add some energy to the system and it has something to play with.
Okay, basically, yeah, maybe we heated it up and it had energy to burn. Yeah, maybe. Matt?
My guess is maybe the atom's not supposed to be there, so if you take it out.
In the middle, you mean?
Yeah.
So maybe it was like an impurity atom. Yeah, so let's say instead of Matt, that like a 1,000-pound gorilla was sitting there, and it was like really like pushing on Zach and Warren next to him and crowding them. So they were happy to have him go, right? Yeah, absolutely. An impurity atom could actually move, and that happens. It doesn't move to the surface; it moves to what are called grain boundaries. We'll describe that later for a similar reason. So, what? Anybody want to give one last shot on this? Why does it happen? It happens. So, what makes energy go down, Jeff?
It increases the randomness.
It increases the disorder, right? An empty seat. That's like having greater disorder, therefore entropy goes up. So it's a balance, right? When you do this, you create more disorder, there's entropy driving it to form, but you're typically costing it energy. Now that said, where you put it on the surface matters, right? Is it just going to appear just speckled all over the place, every here and wherever an atom's just going to appear? Or is it going to migrate to certain spots? They're going to migrate to certain spots because imagine if an atom chooses to sit right there at this kink. Right, the atom diffuses from the middle of the atom, or from the bulk structure, and it sits at the kink. There it's going to have bonds on like 1, 2, 3, maybe 4 different sides. So it won't have the 6 bonds that it would like, but it can still make 4, and that's better, right? So because of this, when you grow crystals, right, and you're moving, either introducing new atoms or you're pulling atoms out of the center by creating vacancies, they will go to specific spots. And you can actually see this. They've taken really clever videos of this happening where they can see that they grow along these edges, right? This edge will keep on growing along there. And then when that's done, it'll start a new one. And then that one will grow along that edge. So they grow in specific ways, and they do so to try and maximize the number of bonds that they can form along the surface. Okay? We can use this though, right? So let's consider a simple cubic structure, right? Just an atom has 4 neighbors in plane, 1 above, 1 below. So it's got 6 neighbors total, right? We can actually calculate the change in energy, and I will not test you on this stuff, right? You will have to use something that comes from it, right? But basically, here's the change in free energy expression. You've got the number of vacancies that it creates times the change in the free energy for each vacancy, right? And then you've got this mixing term, KT times NV, natural log. NV is the number of vacancies, NA is the total number of sites. This term, all here, that big old thing in the square brackets, has to do with mixing, right? So that has to do with this entropic driving force, okay? So we can calculate the number of vacancies from that. Let's see. We've already done that. Let me come back to that. You can get to a plot that looks like the following. Let's just draw this. Okay? If you were going to plot, make sure I get the right thing. Let's say you're plotting percent change versus temperature.
Percent change in what?
We're going to show 2 different things. Right now it's just generic percent change. I'll show you 2 different ones. The first one that we're going to show you is, let's see, this would be delta L. Let me make sure I get this right. Yeah, delta L over L. So that's the change in length. That's the final length minus the initial length divided by the initial length, right? So you've got that, and then you have another term, which might be this one, right? This one is delta A over A. So that's the change in your lattice parameter. So as you heat something up, we know that it's going to continue, for the vast majority of materials, they will get larger, right? They're going to expand. So up till now, we've described that in terms of the potential well, right? We said that there's this asymmetric potential well, and the average position is just getting further and further out. And that explains why delta A over A is increasing. So then the next question is, why does delta A over A not equal to delta L over L, right? So basically, imagine now you guys are all atoms. This big block of students here is all atoms, and I heat you up. The average atom to atom or person to person distance is going to spread out a little bit, right? So this whole block of students is going to swell. And what I'm telling you is that the amount that you swell, which is due to atoms getting a little bit further apart from one another, that doesn't account for the total swelling that we see. That make sense? There's a difference. So what's going on? Anyone want to take a stab at this? It's probably written up here. It's written. Right? So Spencer, what's going on?
You're going to create vacancies and move atoms to the surface.
Yeah, what did we just say last class? We said that vacancies are a thermally activated process, right? So if I give it a little bit of energy, maybe Cody, as an atom, says, I'm ready to make that move, I'm going to become a vacancy. So he picks up and he moves to the surface, right? And by moving from the middle of this to the surface, he incrementally made this thing a little bit bigger, right? So what you can see is between these 2 lines, this difference, that difference right there, we can account for that with the following expression. That difference is equal to the number of vacancies divided by the total number of sites divided by 3. Okay? So basically, the more vacancies you have, the bigger that difference will be. So if you have a material with a really low activation energy for forming vacancies, then your thermal expansion due to your lattice parameter versus your thermal expansion period, there's going to be a big difference between those because you're going to form lots and lots of vacancies. Okay? Can I clarify this at all? Are there any questions about it? Yeah.
Where did that divided by 3 come from?
So where that comes from, good question. So I'm going to skip the math for you guys, but if you work through this, this is our expression for the change in free energy with respect to the number of vacancies that we form. From that expression, you can write what would be the size of your lattice initially. So imagine down at 0 Kelvin, where there's no vacancies, the total volume of your object, you could figure out from your inner atomic spacings, right? In this case, I said NA, that's the number of atomic sites, multiplied by the lattice parameter cubed, right? That would give you your total volume, or L cubed, right? But now when you account for high temperature, where there's vacancies that exist, you have to modify that because the total number of sites is no longer just Na. It's Na plus NV. It's however many vacancies you have, right? So therefore your delta, your L, you can't just use L cubed for your volume. It has to be L plus delta L. So from this expression, we create this. XV, that's your fraction of vacancies, right? Your fraction of total sites. That's equal to NV over NA, and that's equal to 3 times delta L over L minus delta A over A. Okay? Other questions I can answer about this? It's more important that conceptually that you grasp this, that the lattice is going to expand. The atom-to-atom distance is getting bigger, but you're also moving atoms to the surface and therefore making it larger that way. Yeah, Brennan?
So is this how they calculate the activation energy for vacancies of materials? Since now you have NV over NA, you put back to it.
It's a great question. On the homework, you guys will do that. There are better ways to do it. This is one way. This is one way that you could do it. They have better ways of doing it. The problem with doing this is that typically you're talking about very small numbers with vacancies, and when you measure change in length, it's typically not the most precise thing that we can measure, right? You're using tiny little rulers, basically calipers, right? And you're measuring how much these, like literally when they measure thermal expansion, maybe you guys, I don't know if you've seen this or not, you take sort of matchstick shaped sample and you put a little caliper on this end that's measuring it, and as this sample gets bigger, it just pushes that caliper in. Right? It's simple, but surprising that actually works. That's how they'll measure thermal expansion for a lot of things. And it's just not as precise as other measurements, electrical measurements. So the best way to measure vacancies is to relate it to something electrical, like electrical conductivity, which we don't know how to do yet in this class, but by chapter 12 we will. Okay? All right, just a few words on solubility versus solid solutions. No metal is 100% pure. Right? There's always going to be defects. First off, there's going to be vacancies and interstitials. There might be a small number, but they're going to be there. But more importantly, it's just hard to get things completely pure. When you buy them from Sigma Aldrich or Kennecott, when you buy copper from Kennecott or whoever your supplier is, they're going to give you some purity. And it's very hard to get past 6 nines. In fact, if you buy something with 5 9 purity, it already is starting to get very expensive. Like when I buy something, I don't ever buy it that pure almost. We buy things usually 99.9 or 98.5% pure, depending on what the application is, because it gets really expensive, right? Typically because you have to separate these things with slow, tedious processes where you have slight difference in maybe solubility, so you might dissolve out some of your impurities, and you have to do this process over and over. Yeah?
What's the application for something that pure? Is it like scientific, or is there something in the industry?
In industry all the time. So electronics, for example, silicon, they have to get it to 9 nines pure. For like the silicon that your chips are made out of in your computers and phones, that they get extremely pure. So the application is, we'll explain why a little bit later on, but basically an impurity, like an atom that shouldn't be there, that causes properties that you're not interested in. It might reduce the thermal conductivity. So for copper, when you buy copper for heat sinks, if you spend the extra money and get the really high quality copper, then you're able to pull heat out a lot faster of the system that you're working on. In electronics, it's typically electrical conductivity that you're talking about. That impurity atom causes electrons as they're traveling through it to have a collision event which reduces the electrical conductivity, right? There's other reasons. Optical properties, if you want something to be completely transparent, impurities can make a huge problem. The MSc 2010 students made glass last week and found out that adding just a little bit of different dopants, you can color glass very easily with very small amounts. Yeah, Rosa?
If they need to get metal so pure, or just any amount of pure, how do they eliminate the possibility or probability of having or removing?
So great question. Whole classes are taught at in metallurgy. Mike Free teaches a great class on this. I'm not going to go into detail. I'll say that one technique that they can do is electroplating, where basically you start, let's say Kennecott starts out with copper, and it's copper, but it's got a bunch of other stuff in there like bismuth and antimony that you don't want. What they do is by controlling, they set up a corrosion cell, just like we've been talking about, right? They set up one side to be reduced, one side to be oxidized. They connect it. It's got the solution, the electrolyte solution. And then they apply a very careful voltage so that only the copper atoms will dissolve from one side, go into solution, and plate on the other side, but not the other atoms. So therefore, antimony, bismuth, other stuff that they don't want, it will crash down into the solution and sit in the bottom of that liquid solution of your electrolyte. That's one way. There's lots and lots of others, and we just won't get into in this class. Okay? There's a bunch of different alloys which are not pure, but we still use them. In fact, we design them to not be pure metals, right? So these are called alloys or solid solutions. So sterling silver, if you've heard of sterling silver, that is not 100% pure silver. It's silver with about 7.5, I think that's weight percent, I have to double check, copper, right? And the reason they do that is because it makes it harder. If you're gonna make jewelry out of silver and silver scratches and is really soft, you wanna make it harder so it won't scratch. So you add a little bit of copper. It's a cheaper element and it made a better final product. So sterling silver is actually more desirable for some applications. You've got stainless steel where they add 12% chromium. Why they do that is because chromium then forms chromium oxide on the surface, Cr2O3, which forms a passivating layer just like alumina. And therefore now you have stainless steel because it's got this really nice chemically inert layer on the surface. So a lot of these things are designed with some sort of thing in mind, right? Pewter, brass, bronze, copper, nickel, muns. All these things typically have some application. It might be changing the melting point, right, with solder. You don't use pure lead. Actually, they don't use lead at all anymore in solder. They alloyed it with tin because at that composition, it melts at a much lower temperature, right? Okay, so where does the impurity atoms go? You don't have a pure metal. You've got your metal plus something else. Where does it go? Does it substitute one of your existing atoms, right? Do I like pull this atom out and put that new atom where that one was? Or does it sit in between? Or does it order and form a compound, right? So the book gives some general rules, and none of these are hard and fast, but these are all general rules. If you're comparing substitutional versus interstitial, the first factor is size. If it's a very large ion that you're trying to insert in, it's not going to be interstitial. Those are small to start with. So it's going to substitute, right? So again, if I have like a giant gorilla and it's going to have to go somewhere in this block of students, it's probably going to displace a student to sit on that student's chair rather than cram between two students, right? Charge, a lower charge ion tends to be substitutional. The reason for that is if it's lower charge, it tends to be smaller in size. The higher the charge, the higher the oxidation state, like aluminum 3+, right? That's a higher oxidation state. Or titanium 4+ versus titanium 2+, it gets smaller, right? The higher the charge. So the lower the charge, the bigger it gets, so it's going to substitute. They have to have the same crystal structure. If they don't have the same crystal structure, then they tend not to substitute. It's going to tend to form a new phase. And if there's a big difference in electronegativity, it's also going to tend to form a new phase. It'll just form a new compound. So things like copper and nickel, we've seen the phase diagram. It looked just simple, right? Pure copper to pure nickel as a function of temperature. It just did this binary solid solution phase diagram where it was a single crystal structure phase all the way across. The reason for that is because these things are very similar. Size-wise, they're almost the same crystal structure, electronegativity is almost the same, valence the same. So it's not surprising that they can just substitute all the way across. If you take things that are very different, then your likelihood of having an intermediate compound goes up. Okay. And then again, for interstitials, these are typically things that are small, like carbon, nitrogen, hydrogen, small atoms. They are small enough that they can fit in the gaps between your otherwise large atom lattice. Rosa?
So in other like more complicated phase diagrams, do you get all these other compounds and like phases in between? Is that the atoms that don't fit super well together, trying to find a way to fit together?
Yeah, so you're still changing the weight percent, so you're adding them no matter what. But what are they going to do? Are they going to go into the lattice where they're going to cause a lot of strain and cost a lot of energy? Or are they just going to say, you know, it's cheaper for us in terms of energy to phase separate out and form, you know, a lamellar structure, a precipitate, whatever it is. It's going to form a separate phase of not necessarily that pure atom. It might be a mixture. It might be like a 3-to-1 ratio or whatever. It'll be whatever the compound's formula is. But yeah, it's just going to phase separate. Okay, let's talk about something called aliovalent substitution. Aliovalent substitution, this is when you take an ion and you substitute something in that doesn't have the same charge. Say zirconium. Zirconia, ZrO2, zirconium is 4+. You got this +4 zirconium. What if instead of a 4+ ion, what if you use an yttrium 3+ ion and you put it there? What's going to happen? Maybe turn to your neighbor and describe what's going to happen if you do that. Okay, what do we think? You pull out the zirconium and you put an yttrium in. You're going to substitute. What will happen? You want to take a stab at this? Rob, what do you think?
So we figured it would probably, one, throw some kinks in the structure, but more importantly, since it's a free electron, it would make it conductive.
Okay, good guess. Basically, like by putting in something 3+, now you've got this one extra negative charge. Maybe it might make it conductive. So the first rule of thumb with these is that it will always be electrically neutral. So right now, if you do this, if you do the sums, like for every, since it's a 3+ on a 4+ site, it is now not positive enough. Right? Yeah, Rosa?
If you get enough, well, I don't know how to say it very simply, but the system has to be balanced. And so if you get enough charges that add up to like one yttrium add up, then one oxygen will be.
You're absolutely right. It has to be balanced. Charge neutrality, we cannot just leave it at, oh, it's not positive enough and no one cares. It will fix itself, and it has two options. Griffin, did I see a hand?
Oh, yeah, it's exactly.
Same thing. So what are our two options? What can we do? If it's too positive, what can we do? Nate?
You have an interstitial.
Of what type?
Positive. So
Yeah, you could either take maybe another, yttrium and try and cram it in the lattice somewhere. So cation, interstitial.
you have vacancy.
Or you could have a vacancy. What type of vacancy? Yeah, you can have an anion vacancy. Right? Those are your two options. Which one of them is more likely? Vacancies. Because interstitial, that's always cramming something in and crowding the other atoms around. That's typically costs more in terms of energy. So while a cation interstitial is possible, and that exists, it's going to have a higher activation energy for that type of defect than a vacancy. So how many vacancies are we creating? What's the ratio? How many oxygens do we need to remove for every yttrium that we substitute? Oh, almost. Not quite. So for every one yttrium that goes on a zirconium site, we're now not positive by 1, right? We're overly negative by 1, you could say. So if you take out an oxygen, they come in 2-, right, at a time. So then you've overshot it. So you need to remove half of an oxygen for every yttrium. Or in other words, for every 2 yttrium, 1 oxygen goes out. For every 2 yttrium substitutions, 1 oxygen vacancies. Okay? This, I don't remember when this was discovered, but the fact that we know how to do this has led to some amazing, amazing, amazing devices. For example, anybody who drives a fuel-injected vehicle that has real-time feedback, which is it's all vehicles now, and most of them in the last 15 years. So EFI Live, if you heard that, electronic fuel injection live, it's getting real-time feedback. How this works is you have a tiny little oxygen sensor in your effluent of the gas that's coming out of your motor, right? So the effluent, you'd hope if you mixed the right amount of fuel to air in your piston and combusted it, that you would have no oxygen left over, right? That all the oxygen, just the right amount, would combine with the fuel to form your CO2 and water vapor and what other byproducts, right? But if you're running, let's see, rich, and you've got too much fuel, then you've got fuel coming out left over, right? And if you're running lean, then you don't have enough fuel and you're getting excess oxygen left over. So what they do is they put a little oxygen sensor in here. Out here would be air. What's the partial pressure of oxygen in air? Well, it's 21% O2 in air, right? So out there you've got 21%, and if you've tuned this right, your sample gas should be a low PO2, right? You want to have all of your PO2, or your oxygen combining. So what you should have is you have a pathway now, because of the oxygen vacancies, for oxygen to move into that structure, right? Oxygen dissociates as a gas molecule, turns into an O2- ion, so it has to pick up 2 electrons. 1/2 of an O2 becomes an O2- ion when it picks up 2 electrons, right, on that side. And then it travels through your material, and the only reason it can travel through your material is because of those oxygen vacancies, right? If I was like an oxygen 2- ion and I wanted to travel through this group of students, if there's empty seats, it's going to be easier for me to step my way through this group. It's hard if it's just pure students, right? If there's empty seats, it's easy for me to travel through. So by doping it with yttrium, you create empty seats for that atom to hop its way through the lattice and get to the other side where it wants to be, because that's the lower concentration. Yeah, Brennan?
Is it actually like that original atom making it all the way through, or is it like it finds a vacancy and then
It's a steady stream, right? You've got if it's under steady state conditions, which we'll describe in 2 chapters when we talk about diffusion, the rate of atoms entering is equal to the rate of atoms leaving. But yeah, it's not like, it's working its way through. It doesn't have to be the same atom. The oxygen that comes in could be nearby and then Joseph could take off. He could become the mobile species, for example. Okay? But what's important is that without that aliovalent doping that created those oxygen vacancies, zirconia would not conduct oxygen ions. And if it can't conduct oxygen ions, then you couldn't have this redox reaction on both sides of this. So basically this measures like a small voltage, like between these 2 sides. And that voltage is what your EFI live is reading. It's reading a small voltage that you can correspond to a oxygen partial pressure, and you know whether or not you need to change your fuel to air mixture, right? Which is remarkable. This is like dramatically improved fuel efficiency of our vehicles right now. But what's even cooler is that you can do this to create all new types of vehicles. Right now, you can buy the Toyota Mirai, which is a hydrogen fuel cell vehicle, right? And in this vehicle, you've got a tank of hydrogen, right? And you have air. And you have a device, just like one of these ceramics that you've doped, in such a way that oxygen can travel from one side to the other, or you've made it with a different material so hydrogen can travel from one side to the other. Either way works. They recombine. Hydrogen combines with oxygen to form water, and your vehicle has a voltage produced from this. So that voltage is what drives, the electric vehicle, and there's no waste gas. Your only waste gas is water vapor. And more importantly, to get the hydrogen in the first place, you just split water into hydrogen and oxygen to start with, right? So when you hear folks talk about the hydrogen economy, hydrogen fuel cells, solid oxide fuel cells, they're all talking about the same principle. And the principle is you separate 2 gases, so now they have a driving force to move from one side to the other. You have to have a membrane that allows the ions to transport across them, and then you can make all sorts of really cool devices. So when your grandma or grandpa needs oxygen to breathe because they're getting old, the way that they get that oxygen is by taking the 21% of oxygen in the air. They apply a voltage this time, and they're going to take the O2 in air, and they're going to drive it across to over here, to pure O2, right? So they can do just incredible things with this. And if you want to learn more about it, there's courses on that, but that's all we're going to say about it now. But I can answer your questions? Yeah.
I have a question about just a little bit further up about the vacancies and interstitials.
Okay.
Would the structure prefer to just go ahead and take or have a half oxygen vacancy, or would it rather wait once it's overshot for just another cation interstitial?
It will only happen in integer numbers, right? You can't get rid of a half of an oxygen. So yeah, it will wait. For every 2, it will have one of those. Yeah.
How long does it take?
What do you mean?
Just the process
Of substituting atoms and creating vacancies? I don't know that offhand. The kinetics of it are typically very fast, but I couldn't put a number to it or anything. Some things happen very quickly, like electronic interactions, where it's just the exchange of electrons. Those happen instantly. And some of these do take time enough, because I know that it must take some amount of time, because you can quench it and freeze in like a high temperature structure, and you didn't give it time for it to equilibrate to the right number of vacancies that it wanted. But I couldn't put a number on that. I'm sure people have published on it though. Yeah, Rob?
So if you have like 1 vacancy of yttrium, for example, yttrium,
Okay.
Would that, like energetically within the system, would that make it more favorable to get a second substitution, or for that yttrium to substitute back out? Like what is more energetically?
Couldn't say. I couldn't say. Don't know. You have to look at the energies on these things. Okay. Other questions on these, on devices from them? Yeah, Barson?
So is this the same thing for transistors with the vacancies?
We will talk about transistors later this semester when we get to electronic properties. To my knowledge, they don't take advantage of this principle, but I could be missing something that's not clear to me. But we will come back to transistors. Other questions about this? On Friday, my TAs are going to bring a sweet hydrogen fuel cell vehicle, and you can actually see this in action. You can actually start with water and using sunlight or whatever light, or with a battery, you can split that into oxygen and hydrogen, and then when you recombine it, it actually will drive, which is pretty rad. Okay? Yeah, Jeff?
What course did you say that was?
If you want to learn more about it, the Introduction to Ceramics course is the one to take in our department, which I used to teach, but now Shetty does, so you'll learn oodles. Okay, clicker question then. Would niobium 5 plus in TiO2 be substitutional or interstitial? That's our next question. Oh, it's a timer. I'll pause it. Don't panic. I didn't realize I put a timer on that one. Okay. So you put niobium 5 plus, you pull out a TiO2. The question is, does it sit on the TiO2 spot or does it go elsewhere? Is it interstitial or substitutional? Okay, it is going to be substitutional. Interstitial always means that it's going to fit in a spot that's going to crowd things out. If this was a really small atom, it'd be more likely, but it's definitely going to be substitutional. So the next question is, what defect would the niobium 5 plus substitution for the titanium 4 plus site create? Oxygen interstitial, cation vacancy, or self-interstitial? Okay, what's it going to be, A, B, or C? It was definitely B, right? So you put in something that was more positive than the atom that it was replacing. So you're building up excess positive charge. So you can either do an oxygen interstitial, not likely, because that's going to be crowding another atom in, or get rid of one of your other cations, right? So because of this, this creates what we call non-stoichiometric compounds, right? They now, like TiO2 used to be a 1:2 ratio, but by substituting niobium, let's write this as titanium 1 minus X. It's no longer 1 titanium, and now it's 1 minus however much niobium we put on it. Niobium, we can call that X. If this was oxygen 2, that no longer is balanced, so we have to modify this. How do we modify it? Well, for every 1 niobium that substitutes a titanium, that's 1 excess charge. If we were to remove a titanium, we removed 4, so that overshot it, right? So for every 4 niobiums that you put in, you're going to have 1 missing titanium, right? That makes sense? So you have to modify that formula, put it written out. We could write it out. So you would say, it wouldn't be 1 minus X, it's going to be, for every 4 of these niobiums that we substitute, like let's just write 4X there, then this would be 1 minus 5X, right? For every 4 niobium substitutions, you lose those 4 spots plus 1 more, which has to become a vacancy on your titanium site. Okay? Any questions on this? You'll have the chance to write 1 or 2 of these on the homework this week, which is already posted now. It'll be due 1 week from today. Yeah, Arthur? Substitutional means it literally takes the spot where the other one used to be and it sits on that same spot. Interstitial means it crams in between. So again, right, if this is a lattice, interstitial would be somebody like standing right in the intersection of these 4 students. Substitutional says like, could you move over so I can take your seat, sort of thing. Yeah. Logan?
Okay, so if NB5 plus is substitutional because it subs out the titanium,
Okay.
and we're going for charge neutrality, why is it substitutional if it doesn't?
Well, because if it doesn't substitute, imagine how bad that is, right? Because then you've got this. You've got titanium plus niobium X, however much of it you have, plus oxygen 2. So this was already plus 4, and this was minus 4 from those. And you add, for every X that you add, you're adding 5 extra positive charges. Yeah. So interstitial, it's going to still have to create a vacancies to account for it. Right? Like that won't work. That's overly positive. That won't work. Other questions I can answer on this? Yeah, Jeff?
So then, where does the titanium go?
So it's a different mixture, right? You've added, so just like if I took, like, imagine instead of students here, which is like what we have, I had a mixture of students and beach balls, right? If I take 50 beach balls and I make a mixture here, we got just more substance. The fraction changed, right? But we got more substance by adding more, right? You could also take some students out, right? I could pull out half the students and put in 50 beach balls, right? And then I have the same volume of, now it's getting weird. Right? You follow?
Yeah, no,
Okay.
I get it.
Okay. I'll just say one mention about this, that point defects, which is what we've been talking about right now in metals, ceramics, and now polymers. Polymers can also have a point defect. What's a point defect going to look like in a polymer? Polymer are these long chains of repeating units. What would a point defect be, Rob?
Having a different monomer checked in?
Yeah, let's say that you expect your polymer to be polyethylene, so it's this repeating, right, ethylene monomer, right? But let's say one of those got substituted out for a polyvinyl chloride, right? You could think of that as like a point defect. It's a single one, it's one spot where it's occurring. Or maybe one of your side groups isn't what you expect it to be, it's something else, right? That would be a point defect in a polymer. Okay, we got 5 minutes left. Let's talk about one-dimensional defects. These are sometimes called line defects, right? One dimension is like a line, or they'll call them dislocations. So if you look in this picture, this is what's called a bubble raft. A bubble raft. In the 50s, material scientists were all about those bubble rafts. They loved them. This was like, they didn't have the tools to look at actual atoms, so they actually had to make systems that behaved like atoms, and then they looked at those. So they made bubbles out of like soap and water, right? And they said, these kind of behave like atoms. Kind of, right? And when they do this, they said, hey, when we create this raft or this crystal of bubbles, it's not perfect. It has problems. Do you see the problem? There's a couple. So there's one problem right here. That's a missing, oh geez, that's completely invisible. Do I have yellow? Right, so you've got that guy, which is completely just missing, right? But what's going on right over here? Something's not right, right? It's not really in line. So what's happening is there is what's called a line dislocation. There's an extra half row of atoms that got plugged in here. Here's how you can see it, I think, easily. You take and you draw lines like that. Draw this line like that. And voila, we see that there's a problem. You've got this extra half row of atoms that somebody stuffed in there, right? So this is a line defect. It's not a point defect. It's a defect that occurs along a line, right? The line that it occurs along is coming in and out of the board, right? In the example here, bubbles, there's only like one layer because it's on the surface of water. But you could imagine in a crystal where these things are stacked up on top of each other, that would be a line defect that exists all the way in and out of that board along that line, okay? So when we talk about line defects, there's a couple terms we need. First thing is we need to talk about a Berger's vector and a Berger's vector circuit. Here's how it works. You're going to take and pick, you see the defect. The defect is right there. So you're going to make a circuit. You're going to do a circle around that thing and count, right? So let's do this first one. Let's go 3 this direction. 1, 2, 3. Let's do 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Wait, math? Did I do that right? Yeah. 1, 2, 3. And there's a problem, right? I had this missing spot here, right? I'm not linking up. Something's wrong though. Did I draw something incorrect? 1, 2, 3, 1, 2. Oh, I drew that one wrong. No? 1, 2, 3, 1, 2, 3. Let me try this one more time. Let's draw it a little bit larger out. Let's see. Let's do 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, then 1, 2, 3, 4. There we go. So it doesn't match up by one Berger's vector, right? This distance between atom and atom, that is what we call our Berger's vector, right? If that thing wasn't there, then this circuit would match up. Yeah, Larson?
How do you know to start counting with 3s and 4s?
You can pick anything you want. We could have done it way out here. We could have done another one. It'll still give you, it'll be off by one Berger's vector, right? That's the interesting thing about that. The dislocation is just one Berger's vector, which makes sense because all we've done is we've stuffed in one extra half row of atoms right there, right? So it makes sense that's where we're seeing our Berger's vector at, okay? That is what we call a dislocation, and we are out of time, so we'll pick up here next time and talk a little bit more about them.